Hello everyone. I know I'm the one standing between you and food. So I'll promise to be quick. And today I'll be discussing a little bit about one of my works I've been doing during my PhD here with Professor Jonathan Goodman and Alexei Lapkin on AI-driven site selectivity prediction for halogenation chemistry. So during my PhD, I'm analyzing how we can leverage different types of chemical databases, some commercial databases such as Reaxys, high-throughput experimentation databases generated in-house, and also the expertise of chemists, among them you guys. And for that, we're going to use different pipelines from data engineering, different molecular representations, and machine learning techniques to decide what is our predicted product and what's possible side products and how we can identify which one's the major product in one of our reactions. So for example, when we look at chlorination reactions, very standard chemistry, something we learned in undergrad, usually the second organic chemistry course, where you get the ortho, meta, para directing groups. It looks very simple, but if we scale that to a database as large as Reaxys, how does it behave? How we can use that to predict? So we want to leverage these databases with the proper data cleaning techniques to ensure we have the accurate reactions and that we have everything we need in place. We check for the yield of the reactions because we want the major products here. And we identify that for most of them, that big, scary column right here, we have no yield information. And what does that tell us from the data itself? It's very challenging because for some of these compounds, we might have multiple products being formed and we have no information of which one is the major one. And they might be some very interesting compounds that were discovered in a medchem campaign, but they were only isolated in 5–10% yield. So if we just ignore that big bar on the corner there and we look at the data that we have, most of the data that's reported is of non-bias. It's high-yield data. We want to show people that our reactions work. But if we're building models on top of this data, we want to make sure that we have the major products. So an easy way to ensure we only have the major products here is getting everything above 50% yield. So if we have more than 50%, for sure it is our major products. And how much data does that get us? So from our 15,000 reaction IDs, we end up with about 5,000 valid chlorination reactions. And there are some reactions where you have the same starting material, monochlorination, multiple halogenations, or multi-step processes. So if we narrow it down up to monochlorination reactions, something that's very straightforward to model, we get about 3,000 reactions. That's all nice, but what can we do with it? Because when we look at the data, we have our starting material, and because we selected the chemistry, we know what type of chemistry we're running, we have our possible products. So we can generate these algorithmically. So we can put the chlorine on different positions, but still that doesn't give us a prediction. And we can represent that molecule from smiles into a Morgan fingerprint, another way to represent the molecule and to encode all of that molecular featurization. And we can build some machine learning models on top of it to identify the smiles of our products. But still, that doesn't give us a structure, because getting from a smiles or a molecular structure to a Morgan fingerprint, very easy, very straightforward, simple task for chemoinformatics. However, going from a Morgan fingerprint back to a molecule, it is very challenging. There's been some development in the field, but we always have the issues of possible bit collisions, same bits representing different things. But we have our possible products, and we can generate the Morgan fingerprints for them as well, and we can compare them to our predicted fingerprint. And this way, we don't need to get all the bits right. If we have one bit that the model didn't predict correctly, we still have a major, there is one product that's mostly favored, or at least that's more similar to what we predicted. And with that, we built this pipeline where we get the structures of our starting materials up to a decision on what is the major product from our reaction. But let's see how we can play around, because just a box of machine learning models for doing this mapping, it's a bit of an open task. So we evaluated different model architectures with XGBoost and ridge classification being very good tools for this. And because we're always picking one product from a range of possible products, we need to take into account that there is just a random pick baseline. So if we're getting it 25% of the time right, it means we are no better than just random picking. So if we look at different model architectures and different regularization techniques, we see that some of them, let's go a little bit slowly on the plots here. We can see that the further to the right we are, the better the performance on training. But if we are too far away from the dashed line, it means we're overfitting the model because it's performing well on training but poorly on testing. So we want something that's on the line and up high to the right. And if we look at some of the models here, we get many architectures that are quite interesting, but there are also some cases where we just don't have any fit. So that's why it's important for us to evaluate multiple architectures. And once we decide which architecture, it's also relevant to see how large does our representation need to be. So if we're using very, very small Morgan fingerprints, we will have a lot of issues with bit collision when we're generating. So multiple features are occupying the same bit of information, and that doesn't help us predict anything. However, if we go for larger and larger Morgan fingerprints, we're getting more and more information, but that's also a lot more resource intensive. So there is a balance that we can go, and considering we want to build something that's small scale, very fast, something we can run on a laptop or on a web app, we want to keep that in mind and not require 50 gigabytes of RAM just to run one prediction. And also, it's very important to make sure that we're tuning our hyperparameters for the model. And still, again, if we add too much regularization, the model just decides not to fit anything at all. If we add too little, we have a lot more of overfitting, and we want something generalizable. So there is this balance there of how much regularization we are going to add on the model. Now we have all this nice prediction workflow. How well does it perform on other halogens? Because chlorine is one of the multiple halogens we can use to build molecules and to do late-stage functionalizations and do a lot of very interesting chemistry. So we want to replicate this for other halogenations. So fluorinations, chlorinations, brominations, and iodinations. We're not going with anything radioactive down the periodic table. And they all have slightly different baselines and vastly different dataset sizes. So for fluorination, as we see, it's very small data sets because usually we're not exchanging hydrogen for fluorine. But chlorination, bromination, and iodination have a much larger data set. And if we build a Venn diagram for all these four sets, we do see overlaps between all of them. So there are some starting materials that we have data for fluorination and bromination, for example. But what I think is the nicest thing is these areas where we don't have an overlap. It means that there are some structures we know about their bromination reaction, but we don't know about their iodination reaction, and vice versa. So we can play around with this and train a model on one of the halogenations and test it on the others. And if we do this and do it for all halogens, training on each of them and testing on each of them, we do see that the best performances we always get if we're training on one halogen and testing on the same halogen, which means that there might be something that they actually enjoy, if you have a certain scaffold, most likely you have something more similar with the same halogenation. But also we can spot something very interesting. Fluorine is very difficult to predict. Maybe it's because it's a much smaller data set. Maybe it's just because the chemistry is vastly different. And this can go back into the agents that are being used for these transformations. So while for chlorine, bromine, and iodine, we usually have the succinamides and the halogens themselves, fluorine is F2. It's highly reactive. It will burn through a lot of things. So there are other halogenation agents, and the mechanisms might be much more different than what we usually see for chlorine, bromine, and iodine. And we do see some slight differences from going from chlorine to iodine. Might be because of the conditions, and the reagents might guide us towards a different mechanism on some cases that we do see a small difference in their accuracies. But we want to have one model and not 4 models. We want something general. And we can combine all those data sets and remove the overlaps and any issues with consistency. So for example, something that reacts one way with chlorination, something that reacts another way in a bromination. We don't have many cases of those. They're very atypical. But we end up with a much larger data set of almost 18,000 reactions. And we can, again, do this training and testing, looking at the different halogens and this new superset. And the nice thing is that fluorine, we're leaving it out. It's too odd. We don't have enough information about it. But we were able to build one model that performs well across all the halogenations from chlorinations, brominations, and iodinations, which is amazing. So halogenations are solved. So if they're solved, quote unquote, how much data do we actually need to solve all this? Looking forward to other transformations. And if we go and look at how much, if we just split the data and train a model on different data set sizes, what we see here on the left is that the larger the data set, the better it is, but it starts to plateau. About 8,000 reactions looks like it's as much as we can get. It might be because of diversity of the data set. So after 8,000 reactions, we need something that's wildly different from what we've seen before for it to actually contribute to anything. But one of another nice feature is that as we go, towards larger data set sizes, we also have less overfitting. So the more data, the better, but we can do a lot of work and get a lot of results with smaller data set sizes. And let's say you want to use this fantastic model and have this molecule up top here. I want to give you a second to think, where do you think it's going to react? Because it's not much of a standard first or second year undergrad molecule that you see in an exam. And we built a web app that people with the stakeholders, they could use it, having access to the reactions data themselves. So this is not online, but it's built. It just has no model on the online version. And you can input your new molecule, let's say this complex target, and it will run the prediction for you. This is not sped up, so it's on the web version, and the prediction is pretty much quick and straightforward. Few seconds for a web page to generate the molecules that you're interested in, and you can identify what is the reaction site. But I don't care how well an AI model performs. I want it to perform better than what we have nowadays. We want something better than what's available. And one of the main things that's available is chemists, people with a lot of expertise and knowledge and years of training with all of this data. So one of the benchmarks that we're collecting is a quiz, an online quiz. So you can access it through the QR code or the link below. And you can fill it yourselves. It will show you 5 reactions from our test set. So these are reactions extracted from Reaxys that we got the OK to share. And you can test how well do you know your chemistry or your chlorination, and you can beat the AI model on it. And we want to populate it with a little bit more data and also have this benchmark that so far the machine learning model has been outperforming humans, but maybe it will change after your responses. So I'm very much looking forward to having your inputs as well. It's a bit of a collaborative experience here. So as a conclusion, we have built and optimized the model for reaction prediction, in the case for halogenation, and making this data, enhancing this data from chlorine to other halogens. And the more data, the more helpful it is with diminishing returns. And we also built some easy-to-use web interfaces for using the model and to collect some benchmarks of this reaction. And with that, I want to thank my supervisors, Jonathan Goodman and Alexei Lapkin, and funding sources and UCB Pharma, who's been very helpful in the development of this project. And open for questions.